So 2 weeks ago, we talked about ionic bonds, and we basically talked about it with the question, will it ionic bond, right? Do you remember that? And so we asked that question, will it ionic bond? And the answer was yes, as long as what is true? One forms a cation, one forms an anion. Okay? So if one is positively charged and one is negatively charged, they will ionic bond. But the question we need to address, and this will kind of clue you into what a covalent bond is what if they won't ionic bond? What if they won't? What if they won't ionic bond? So it gives you this sense that there's something unique about a covalent bond. It is not an ionic bond. So let's talk about it. What is it then? Now, you need to remember that cations will form ionic bonds with anions, right? I just mentioned that whenever that is the case where you have a cation and an anion, the answer to will it ionic bond is going to be yes. You also need to remember that every atom wants to have 8 electrons in its outermost energy level. That's what every atom wants. Every atom wants to have 8 electrons in its outermost energy level. That's what every atom wants. So we talked about this 2 weeks ago. How does a cation get that? What did a cation do to get 8 electrons in its outermost energy level? If it's a cation, it has what type of charge? Positive or negative? Positive, right? You'll remember that because cation should be pronounced cation, which makes you think vacation. And that's a very positive experience. Okay? So if it's positively charged, that means it did what? Did it lose electrons or did it gain electrons? It lost them. Okay? So a cation accomplished this by losing electrons. How did an anion accomplish getting 8 electrons in its outermost energy level? Took them from something else. Took them from something that became a cation in the process. Okay? And so these are how ions form. You can't just take, and I mentioned this 2 weeks ago, but I want to remind you, you can't just take an electron that's floating freely around the ethos. Okay? Because there aren't electrons floating freely just in the muck that is the atmosphere. Okay? And so, yeah, in order to even form ions, if you are a cation, you have to find something to take those electrons. You can't just eject them and like, ooh, got rid of those electrons, whoop-de-doo, got what I wanted. No, you got to find something to take it and become an anion in the process. And then you end up attracted to that anion because you're positively charged and they are negatively charged. Okay. By the way, we call these electrons in the outermost energy level, we call them valence electrons. Ooh, that's going to bother me. That clock is not right. Okay, so we call these valence electrons. So there's one more piece of information that we need, and then we can talk about covalent bonding. All right? And that is an atom's ability to attract electrons to itself is called electronegativity. So an atom's ability to attract electrons to itself is called electronegativity. Again, an atom's ability to attract electrons to itself is called electronegativity. So let's think about this. Are atoms that form anions, are they going to have a low electronegativity or a large electronegativity, a high electronegativity? If they form anions, do they have a good ability to attract electrons to themselves or a poor ability to attract electrons to themselves? Good, right? They're becoming anions. They're taking on extra electrons. So which means the atoms or the elements that become anions are going to have a high electronegativity. Conversely, the elements that become cations are going to have a low electronegativity. Okay? All right. So now let's get into covalent bonds. If two atoms that both tend to form anions interact, and both those atoms want to have 8 valence electrons, what they're going to have to do is they're going to have to share electrons. They can't transfer the electrons because they both tend to become anions. They both are electron hogs, if you will, with high electronegativities. And so they've got to share electrons. To where some of the time one of them gets the electrons, some of the time the other one gets the electrons. Does that make sense? And then conversely, if two atoms with low electronegativities, or you could say two atoms that tend to form cations, interact, they must also share electrons, but that's a different kind of bond. Okay, that's one we'll talk about next week. The metals. Okay, so one important point to keep in mind, when they share electrons, they do not become ions. Okay, when they're sharing electrons, they do not become ions. Even though you took two things that tend to form anions, and they're going to share electrons, they do not become anions. They do not become ions. They're sharing electrons. They haven't fully taken those electrons to their private space, if you will, their exclusive space. Does that make sense? Any questions? All right, so let's answer this. What if they won't ionic bond? The best way to answer that question is to just say this: they may covalent bond. What if they won't ionic bond? Answer it: they may covalent bond. And then if you want, you can put in parentheses, share electrons. You don't have to, but if you might want to remind yourself what a covalent bond is, that sharing of electrons. Okay, a couple of key terms from here. I would like for you to look up valence electrons. Valence electrons. It's that indented point about a third of the way down. And I would also like you to look up electronegativity, which is in the next line. So I'd like for you to look up valence electrons and electronegativity. And look them up outside of your textbook, okay? In another resource. Okay. You all right so far? All right. So we've seen this periodic table many times. And I wanted to show it to you again so you can think about which electrons in which types of orbitals tend to be shared versus, otherwise. All right, so we've already talked about that atoms that tend to form cations, like these, right? These are atoms that are typically going to lose electrons to get the 8 valence electrons that they want. They're going to tend to form cations. They have low electronegativity. Atoms over here that are going to tend to form anions, taking on extra electrons, they have high electronegativity. And so we know that electronegativity is going to increase as you move left to right on the periodic table. But what about up and down? Okay? So if you're going to think about it this way, of all of these atoms here, okay? So here we've got, let's say if we're dealing with, do I have a meter stick that I can reach all the way up there with? Nope. Where's my, man, I usually have one of those things that I can use up here. All right, anyways. So if we're up in this column here, but all the way at the top, that's nitrogen, right? If you're looking at your periodic table. And so nitrogen has 3 electrons in that 2p shell, right? And so for it to get all 6, it's going to have to gain 3 electrons, right? That makes sense? Okay. Then if we look in this column, and we go all the way to the top, that row 2, that's fluorine. Fluorine's got 5 electrons in the 2p subshell. So for it to get 6, it only needs 1 more. And so I want you to think about this. Using the context of if you're saving up money to buy something. Have you ever saved up money to buy something? When are you most interested in saving the money? When you're really far away from what you want to buy, or when you're really close? When you're really close, right? I used this illustration on Monday, and I would love to buy a soft serve machine. I would love it. But they're really expensive, and I've not really started saving for it at all because it's really expensive. I'm really far away from buying a soft serve machine. But let's say my dad was like, you know what, I want to give you a very significant amount of money towards your soft serve machine. And he gave me like 90% of the money I needed to buy my soft serve machine. He's like, I don't want to buy it for you. I want you to have to work for it, right? So that you appreciate it more. That's what a great dad does, right? And so now I would start, man, if I was 90% of the way to getting there, I would start really thinking seriously about saving money for that soft serve machine. They're about $8,000. So if I was 90% of the way there and I was $800 away, like, man, I'm going to start really putting aside some money every month to get myself my soft serve machine. I don't even know where I would put it, but I would find a place for it, maybe in the garage. You just walk out there, fill yourself some soft serve. Anyways, that's another story for another time. Okay, so fluorine is going to have a higher electronegativity than nitrogen because it's really close to getting what it wants. Plus, we already got this feeling low electronegativity here, high here, gives us this feeling it's increasing as you move left to right. Well, that's about as right as you can get before you get to elements that they already have what they want. They've already filled their outermost energy level. Okay, but what about this? What do you think about fluorine versus something down here? Astatine is I think what it is. In row 6, this position here. Okay. Which one do you think has a higher electronegativity, fluorine or astatine? They are both 1 electron away from getting what they want. Do you think there's any difference? Do you think they'd have the same electronegativity? Who thinks same? By a show of hands. Who thinks fluorine would have more? Who thinks astatine would have more? Who doesn't have a thought? There are 2 of you that haven't raised your hands, okay? So fluorine has the highest electronegativity of any element on the periodic table. It has the highest. The reason why fluorine's electronegativity is higher is because that 1 extra electron is a pretty big deal to fluorine. How many total electrons does fluorine have? Look at the number in the top right corner. 9. So in a neutral version of fluorine that hasn't become an ion yet, it has 9 electrons. If it gains 1 more, it gets what it wants. Now that 1 electron is 10% of its total electrons, right? Because it gains that 1 more, now it has 10 total, 1 is 10% of 10. Yes? Now look at astatine. How many electrons does astatine have? 85. It gets 1 electron, it gets what it wants. But now that 1 electron is a much smaller percentage of the total number of electrons it has, right? And then on top of that, if it has that many electrons, that 1 added electron is going to be really far away from the nucleus, where the positive charge is, right? The more electrons you build, the bigger this cloud becomes around the nucleus of the atom. And so that electron's much further away from the atom. Okay, so electronegativity increases as you move left to right and as you move bottom to top. So fluorine has the highest electronegativity. Chlorine is high, almost as high as fluorine. Oxygen is high, almost as high as fluorine, right? So we're getting that left to right, it increases. Bottom to top, it increases. Oxygen and chlorine, I think, are about the same. Chlorine might be a little bit higher. All right? So we have another question to ask, and it's this one. How do we know which electrons will be shared? So we know they're going to share electrons if you've got 2 atoms that tend to form anions coming together. They're going to share electrons, but how do we know which electrons they're going to share? That's a wonderful question. This very well might be the best question I've asked you all year. How do we know which electrons they're going to share? All right, first point. The shared electrons must be in the outermost energy level. So the electrons that are going to be shared must be in the outermost energy level. So that is, only valence electrons can be shared. Only valence electrons can be shared. All right, that kind of makes sense, right? Only the outermost electrons are going to be able to share. On top of that, we can draw what's called a Lewis dot structure to show which valence electrons are in an orbital by themselves. We can draw a Lewis dot structure to show which valence electrons are in an orbital by themselves. Did you pick up on the interesting feature of this sentence? What's the most interesting part of this sentence? What's that? Draw? You're like, that sounds pretty interesting. In an orbital by themselves. And what question did we ask at the top of the slide? How do we know which electrons are going to be shared? And we answered it with a sentence that says we can find electrons in an orbital by themselves. So which electrons do you think are going to be shared? Those that are in an orbital by themselves. That's interesting. That is interesting. At least for covalent bonds. Give you a moment to write the rest of that down. I know I was talking in the midst of it. All right, so you need to remember that we have to fill the s orbital in an energy level before we can start putting electrons into a p orbital. We have to fill the s orbital in an energy level before we can start putting electrons into the p orbital, right? Into a p orbital. You remember that? We have to fill the 4s before we can start putting electrons in a 4p orbital. On top of that, you need to remember this. There are 3 p orbitals that are all in the same energy level, and that electrons remain unpaired as long as possible. Right, you all saw this on your worksheet. We talked about this during our class time together. You saw it on your exam, I think. Okay, remember that there are 3 p orbitals that are all the same energy and that electrons remain unpaired as long as possible. Sound good? So how do we know which electrons will be shared? The best way to answer this question is to write this. We draw a Lewis dot structure. We draw a Lewis dot structure. We draw a Lewis dot structure. Give you a moment or two to finish writing down any of the lines you haven't written down yet. We've answered this question. We've got all the points on the slide. Now, what are you thinking? The way I just answered that question, what are you thinking? You thinking like, I don't know how to draw a Lewis dot structure? Like, that sounds like a wonderful way to answer this question, but Dr. Engel, I have no idea what a Lewis dot structure is. Anybody thinking that? Let's do it. So we're going to draw a Lewis dot structure for oxygen, for nitrogen, for carbon, for phosphorus, and for chlorine. And we're going to draw the Lewis dot structure for these 5 elements. And notice we are restricting this to elements that are going to tend to form anions. These are elements with high electronegativities, relatively speaking. Carbon's is actually pretty low, but it's higher than something like sodium. All right. You ready? Okay. So here's our trusty periodic table we've used so many times. And we go to oxygen. Oxygen sits right here on the periodic table, right? So according to this, it has 2 valence electrons in the 2s orbital, and it has 1, 2, 3, 4 more in a 2p, some type of 2p orbital, right? So oxygen has a total of 6 valence electrons. 2 in the 2s, 4 in a 2p, okay? So when we draw the Lewis dot structure, the only electrons we care about are those valence electrons, the electrons in the highest energy level. And we're always going to do this. Some people have different strategies. My strategy is the best, okay? So we're going to do this. We're going to go ahead and we're going to draw the 2 electrons that are in that s orbital right on top of that symbol. Okay, so our symbol for oxygen is O. We're going to draw the 2 electrons in that s orbital right on top of it. And we know that they're paired because there's only one s orbital, and every orbital can hold as many as how many electrons? 2. Okay, so that orbital was full. Now we can start putting electrons into a p orbital. And we're going to have one p orbital on the left, one p orbital on the bottom, one p orbital on the right. Okay, and we're going to keep these electrons unpaired as long as possible. Okay, so we're going to put one here in 2px. We'll put one here in 2py, and we'll put one here in 2pz. Okay. Have we accounted for all of the valence electrons? No, we've only accounted for 5 of them. And how many does it have? 6. Now we have to pair one up, right? We've got to put a second electron into one of those p orbitals. Doesn't really matter which one you do because they're all the same energy, right? So I'll put it here just for convention because that's where I started. So I'll put it here on the left. You're like, Dr. Engel, why are we going counterclockwise with your strategy? Why? Because clocks are so boring. So we're going to go counterclockwise. We're going to be a little different, a little spicy. Okay? Like, so if a clock ran backwards, would that be better? Maybe it would.
And that's the way you run out of track, so.
Yeah. Yeah. Well, that's the way, like, when you set a timer, it goes backwards, right? And that gets you, like, man, this is really pumped up. Like my kids, I can tell them, wow, you need to clean your room because you trashed it. And they just like slowly take hours. And then I'm like, all right, you have 5 minutes to clean your room. Everything left on the floor is going to the Goodwill. You set that 5-minute timer, man, something magical happens. I've never seen a kid move so fast. Did your parents ever do that with you? Oh gosh, it's great. Okay, so we have 2 unfilled orbitals, right? And we just learned in the previous slide, those are the electrons that get shared. So which means if this oxygen wants to get 8 valence electrons, it's going to share this one, and it's going to share this one. And when it does, it's going to share it with something that it can share an electron from an empty or a half-filled orbital on that element, and then both of them have access to a fully filled orbital. Isn't that awesome? So oxygen, these are the electrons it's going to share. And again, when it does, it's going to share it with something that also has a half-filled orbital so that they both have access to a fully filled orbital. And they both get what they want, filling all of those highest energy orbitals. Okay? So when oxygen forms covalent bonds, how many is it going to form? 2. 1 to fill this orbital, 1 to fill this orbital, 2 covalent bonds. Okay? When oxygen forms a covalent bonds, it's going to form 2. And now it's going to have filled p orbitals in its highest energy level. And it's going to be happy. It's going to be super happy. All right, now nitrogen. Nitrogen is right here on the periodic table, right? So it has 5 valence electrons, 2 in the 2s, and then 1, 2, 3 more in 1, 2p orbital, okay, in spread throughout. Okay, so nitrogen will do the same thing. We'll draw the 2 electrons that are in that 2s. And now we have to account for the 3 that are in a 2p orbital. And they will remain unpaired as long as possible. So we will get 1 here in the 2px, 1 here in the 2py, and 1 here in the 2pz. And now have we accounted for all of them? We sure have. And so which electrons is nitrogen going to share? All of these. All of the half-filled shells. So when nitrogen forms covalent bonds, how many is it going to form? 3. 1 to fill each of those half-filled orbitals. And again, it has to bond to something that can also have a half-filled orbital. It's good stuff. Let's skip carbon for a minute, because carbon's going to be one where it's going to blow your mind. It's going to be the best and the worst thing you've seen today at the same time. Right? It's like finding out, I don't know. Oh, that would be sad, actually. It's like finding out somebody ate your sandwich. Right? That's horrible. But let's say this. Somebody ate the rest of your sandwich, right? You ate half of the sandwich, somebody ate the other half. Right? That's horrible. But you know what that means? You get to make something else for lunch. So it's both the worst and the best news. You're like, now I actually get 2 different things for lunch. Half of the sandwich I already ate. Something else. You're like, nobody ever touches my sandwich factory. There are 2 rules that I live by. And these are completely absurd. These are not really the 2 rules that I live by, but I think they're funny. This is what I like to share with people. The 2 rules that I live by. Never take a big man's food. Okay, that's the one order. And then the second rule is to follow rule 1 again. Okay, really make sure you follow rule 1. Okay? Never take a big man's food. It's dangerous. Okay, sorry. So we're going to skip carbon. We're going to go phosphorus. So phosphorus sits right here on the periodic table, right? Okay, so like nitrogen, phosphorus has how many valence electrons? 5. 2 that are in 3s and 3 that are in at least one of our 3p orbitals. Okay, so we'll do those s electrons right away. Now they're in a 3s instead of a 2s, but it is an s orbital. And then we have how many more valence electrons? 3, and we'll keep them unbonded as long as possible. And it'll look something like this. And so which electrons is phosphorus going to share? These 3 electrons again, and it's half-filled orbitals. So when phosphorus forms covalent bonds, how many is going to form? 3. But what you'll find out is phosphorus does something crazy. Phosphorus actually forms 5 covalent bonds. It gets all of these involved. How that exactly works, you're not ready to handle yet. But just suffice it, this tells us phosphorus should make 3, and it should. But it makes 5. Okay? And sometimes it does only make 3. All right, chlorine. Chlorine sits right here on the periodic table. Right? So it has how many valence electrons? 7. It has 5 of them in the 3p subshell, but it has 2 more in the 3s, right? So it has 7 total. We'll do those 3s electrons first, and then we'll take our 5 remaining and we'll start putting them into a 3p. Here's 1, here's 2, here's 3, but we have 2 more we need to account for. Now we've got to start filling these half-filled orbitals just to account for all the electrons chlorine has. Right? So chlorine has how many half-filled orbitals? Just one. So this is the only electron chlorine is going to share. So when chlorine forms covalent bonds, how many will it form?
1.
And this one is just one. It doesn't do something like phosphorus and just completely violate the rules that you know. Right, but there's always something that breaks the rules, right? That's where the saying rules are made to be broken come from. It doesn't really come from like a vile child. It comes from the natural world. Anyways, sorry. Now let's go carbon. So carbon sits right here on the periodic table. It has how many valence electrons? 4. Okay? 2 of them that are in the 2s, we'll draw those first. And then 2 more, one of them that's here and one of them that's here. And you're like, Dr. Engel, why can't we move that one there to keep them unpaired as long as possible? Why can't you? This is a lower energy level than this, and you have to fill this before you can start putting electrons here. Okay? So, but it can only share electrons that are in a half-filled orbital, which is just these 2. Right? And you're like, cool. So carbon will do that, it'll share those 2 electrons, and let me show you this. So let's say it forms covalent bonds and it shares 2 electrons from some other material that has a half-filled orbital. I drew these electrons red because they didn't originally come from the carbon. Right? Does that make sense? Okay? And you're like, cool. Carbon's happy. Is carbon happy? Why not?
It has the extra p orbital.
It's only got 6. But how many does it want?
8.
8. And you're like, oh man, what's going to happen here? Well, can't it just share something with another element? Like, let's take oxygen. Oxygen's got a half-filled. But then if it shares that one, it's only going to have 1 electrons that it's sharing. The oxygen didn't gain anything from making that bond. The carbon sure did, but the oxygen didn't. Why is the oxygen going to want to make that bond? The oxygen still has only 6. The carbon has 7 now, so it's getting closer to what it wants. You're like, wow, we've got a dilemma here. This is where the mind-blowing comes. So what happens here is something that should not be able to happen. And it doesn't happen unless you go to make bonds. So it doesn't happen in just, carbon chilling by itself. But when that carbon goes to make covalent bonds, one of these electrons moves to here. Because that shouldn't happen, right? This is lower energy than these. But that's the only way carbon can get what it wants. So it makes something happen that shouldn't happen. But it happens to make a bond. Okay? And one thing you need to learn about chemistry is atoms will do things that they should not be able to do to make bonds. And the thing is like we just don't understand the chemistry enough. And we're still trying to figure out how this works. We have models to predict how it works, but the models aren't great. We're still trying to figure out how this works, but this is what must happen in order for carbon to be able to fill its valence shell. So when carbon, then if this moves over there, then we've got 4 half-filled orbitals, and then carbon will make how many bonds when it makes covalent bonds? 4. Which makes carbon a wonderful element to build really big, complex chains of atoms. Because it makes 4 bonds. And it does, every time. Every carbon atom involved in a molecule makes 4 bonds. 4 covalent bonds. That's cool, right? Any questions about that? So I told you it was going to be both the best and the worst thing you've seen today. It's the best because you're like, wow, it's really cool. But it's the worst because you're like, Dr. Engel, you told us we got to fill that S before we can put them in P. And now we're going to take something that's in an S and put it at a higher energy level? How's that going to work? The only way it's going to work is if something really good can happen, and that's the atom getting a fully filled valence shell, fully filled outermost energy level. And because when it has that, all of the electrons become very stable. Okay. We have one more question to deal with, and then we will be done. What if the atoms sharing electrons have different electronegativities? What if the electrons, or the atoms sharing electrons, have different electronegativities? So they're still sharing, but some of them are better able to attract electrons than others. The answer to this is somewhat simple, and so I will give it to you in the very first point on this slide. Let me know when you're ready for it. Now, some of you are still writing this question. What if you're like, Dr. Ingo, write shorter questions, and then it won't take us so long to copy them. You're right. My brain is incapable of asking short questions. It's also incapable of answering questions simply. I have to work very hard to give succinct answers. Anyways, the simple answer is this. They share the electrons unevenly. That's what happens. If two atoms sharing electrons have different electronegativities, they share the electrons unevenly. And here's what that actually means. The atom with the stronger electronegativity gets to spend more time with the shared electrons. They're still sharing them, but the atom with the higher electronegativity is spending more time with those shared electrons. Can anyone think of an analogy for this? For an uneven sharing of something?
It's like if one kid is stronger than the other one, so he gets the toys more.
Yeah, right? So the way I think about it is this. So I think about identical twins. And there's usually a dominant twin, right? Like a more outspoken of the two. But the twins, I'm thinking like twins share a room, that's probably going to be a pretty even sharing of that room, right? They're identical twins. Two brothers that are 2 years apart, where one outweighs the younger brother by 100 pounds. That was my reality. It's not an even sharing of that room. I shared a room with my brother for 15 years, until I was 17 and he was 15. If you walked in that room, other than there being two beds, you would have no idea two people shared that room. Because everything in there looked like it belonged to me. I decorated the room. Okay, the room looks like the way I wanted the room to look. Even my brother's bed looked like the way I wanted my brother's bed to look. So we shared that room, but I spent a lot more time with that room than he did. I don't even know what he did during the day. I hung out in the room, reading, doing whatever, watching TV. Actually, I didn't have a TV in my room. Reading, listening to music. I don't know where my brother spent his days, honestly. Maybe with my mom somewhere, complaining about not having a bedroom to hang out in. So, it's a good analogy. It's a really good analogy because you're like, okay, they're sharing that room. So it's not like I took the room and kicked my brother out, right? That'd be like an ion situation, right? I took both beds and he got 0 beds. And so we both got what we wanted, right? The analogy broke down, but it's okay. It's a pretty decent analogy. Now, this situation can create a polar molecule. It doesn't always create a polar molecule. It will always create a polar bond, but it will not always create a polar molecule. But this can create a polar molecule. And so what do you think of when you hear the word polar? Cold, polar bear. Anybody think North Pole, South Pole? Joe.
I think 2 poles of a magnet.
2 poles of a magnet, right? Where there's something distinct about it, right? The North Pole has polar bears and no penguins. The South Pole has no polar bears and penguins. Coincidence? Probably not. Because I think a polar bear would love to get down on a penguin, right? But anyways, there are seals in both, and the polar bears have plenty of seals to eat. You don't need to worry about the polar bears, except for the fact that the ice is disappearing, and that's kind of rough for polar bears. Anyways, and so polar molecules, there are 2 distinct ends, 2 distinct poles. You have a positively charged pole and a negatively charged pole. Okay? And so they're still sharing the electrons, but one atom is getting a lot more time with those electrons than the other. And so it creates actually a negative pole. And the atom that's getting less time with those electrons is on the positive pole. And so polar molecules become attracted to other polar molecules and form what are called hydrogen bonds. Polar molecules are attracted to other polar molecules and they form hydrogen bonds. Which pole on one atom is attracted to which pole on the other? What do you think? Because you know from chemistry that what types of things are attracted to each other? Opposites. So the positive pole on one molecule is attracted to what? The negative pole on another, forming these hydrogen bonds. Polar molecules are also attracted to ions and will dissolve ionic bonds, will dissolve ionic compounds, will break these ionic bonds. And that makes sense, right? Because if it's polar, it's got a positive end, it's got a negative end, it should be attracted to ions, right? The positive end should be attracted to what types of ions? Negatively charged ions. And what do we call those? Anions, or anion, which makes you think onion, which makes you cry when you cut it, right? It's negative. I mean, they are delicious, but they do make you cry when you cut them. You can put on some goggles like you would wear in a swimming pool, then you'll be fine. It's because the onions emit an acid, or they emit a gas when you cut them that when it mixes with the fluid of your eyes, forms an acid. That's why it burns and makes you tear up. Anyways, sorry. And then so the negative pole of a polar molecule is going to be attracted to what? A cation, right? A positively charged ion. Have we seen this happen before? Where an ionic bond was broken inside of a polar molecule? Yeah. Dissolving salts in water. So water must be a polar molecule, and it is. Water is a wonderful example of a polar molecule. Water is a wonderful example of a polar molecule. And it does a wonderful job of breaking ionic bonds and dissolving ionic compounds. Now look at your periodic tables. Where is water? Or where, sorry. Water is not on your periodic table. What is in water? What elements? Oxygen and hydrogen. Where is oxygen on the periodic table? Over on the right. High electronegativity or low electronegativity? High, right? Tends to form anions. It's an electron hog. High electronegativity. Okay. Other than fluorine and chlorine has the highest. Okay. And it may actually be just as high as chlorine. I don't know. I'd have to go look at the numbers. What about hydrogen? Where's hydrogen? All the way over on the left. High electronegativity or low electronegativity? Low. So you've got oxygen, an electron hog. Hydrogen, an electron, and just very giving with its stuff, right? It's the younger brother. In this case, there are two younger brothers for every one older brother oxygen, right? So maybe like twins, younger than the older brother. They all share a room. Okay, so oxygen is going to spend a lot more time with those electrons than the hydrogens are. So which part of a water molecule is going to be negatively charged? Oxygen. And which part's going to be positively charged? Hydrogen. So the oxygen from one water molecule is attracted to what in another water molecule? The hydrogen, the positively charged pole. That's cool, right? And so because water is polar, it can do some very, very, very wonderful things. Like dissolve salts, because you need the individual ions to carry out reactions in your body. Because water is polar, water is more dense as a liquid than it is as a solid. That's great, because if it wasn't that way, when ice froze at the top of a body of water, which is where it's coldest because it's interfacing with the cold air, and after that block of ice formed, it would sink all the way to the bottom.
And more would freeze.
What's that?
And then more would freeze and keep going.
Yeah, and more would freeze and would just keep going, but anything living inside that body of water would be crushed by this ice dropping to the bottom. That doesn't sound great for a fish that lives in that lake that's freezing over, right? So you just freeze over, you crush all those fish, the next year you got to start all over. Let's restock the lake. Okay?
Got a lot of fish to eat, though.
You do have a lot of fish to eat. Water molecules stick together. Another wonderful thing is it means at the surface of water, you get something pretty cool that happens. And your worksheet actually asks you to carry out an experiment. And I ask that you do it. It's very simple. You should be able to have no problem finding the materials in your house to do it. And you'll be able to see this surface tension. Because water molecules want to make hydrogen bonds with other water molecules. But at the interface of water and air, there are no water molecules to make hydrogen bonds with those water molecules. So all of the hydrogen bonds the water needs to make are happening to the side and below it. And what it makes is the surface of the water really sticky, relatively speaking, to lower levels. And allows some things to walk along the water surface. Like the basilisk lizard that runs along the water surface. Or water striders, insects that walk along the surface. Or Jesus, like walking along the surface. But that was obviously very miraculous because Peter came out, did it for a moment, and then he got scared and started to sink, right? Okay, but this is all cool things about water that are only true because water is a polar molecule, right? And why is water a polar molecule? Because oxygen and hydrogen have different electronegativities. Oxygen's electronegativity is much higher than hydrogen. Water, the molecule of water is about as polar as you can get before oxygen would just completely strip the electrons away and form an ion that would then be attracted to hydrogen ions. Water molecule is about as polar as a molecule can get. If it got any more polar, the electrons would be completely stripped away and it would become an ionic compound. Okay? That makes sense? This makes water wonderful. Which makes life work, which is wonderful. All right? Any questions, thoughts, concerns, snide remarks? All right. Have a wonderful day. Enjoy the rest of your Wednesday.